So welcome back. What we're going to do today is we're going to just take you through all of the circle geometry theorems that we expect you to know, and so we'll basically dive straight into those. From there, we've done all the new work and we just need to practice. Okay, so we're not going to be in our workbook today. We're just going to talk you through these different theorems. So the first one says that if we take a line from the center of the circle perpendicular to a chord, it bisects the chord. In other words, it cuts the chord in half, and we can see that. The converse is also true. So in other words, if we go from the center to the midpoint of the chord, that will always be a right angle. Okay, so we can see no matter where we draw this, those two things happen together. In other words, if it's perpendicular, it bisects, and if it bisects, it is perpendicular. The second one has got to do with what we call the angle at the center theorem. And what happens is that the angle at the center is always double the angle at the edge. All right, now they actually, so we can drag this and we can see the angle made from points C and D at the center is twice the angle at the circumference. Okay, all right. There are actually four different flavors of this sketch. Okay, that's the first one. All right, some people say they call it the rocket theorem. Okay, angle at center theorem is its proper name. All right, don't worry about the fact that these aren't exact in terms of being double, but that's just a rounding issue. Okay, but another sort of flavor of this is that if we drag this here, it now doesn't look like a rocket at all, but let's just follow from point C and point D. There's an angle at the edge at A, and there's an angle at the center, and the one at the center is twice as big. So that's kind of a second version of that. Third version is this one where it's moved right around like that. Okay, notice from C and from D we've got an angle at the center and we've got an angle at the edge. The one at the center is twice as big. This looks nothing like a rocket, this particular version. Okay, right, so that's the sort of third version. Some people think this looks like angles in same segment. It's not. All right, angles in same segment, all 4 points on the edge. The final version, all right, in fact, there are actually kind of 5 versions, but we'll talk about the fifth one separately, is if we drag this angle at the center to be a reflex angle, all right, then the angle at the center is twice the angle on the other side here. All 4 of those flavors are angle at center theorem. Okay, this is not a cyclic quad that we're looking at here. A cyclic quad has got all 4 corners on the circle. Okay, let's just go back over those again. All right, so kind of flavor number 1. All right, flavor number 2, where this is actually in line like that. Flavor number 3, where it's kind of around the corner like that. And then flavor number 4, where it's kind of reflex like that. Okay, you need to be able to pick all of those. Okay, flavor number 5 is actually, this is a special case of the angle at center because this angle over here is 180 degrees. So this is coming off a diameter, all right? And so the angle at the center says that this must be a half. Right, this is called an angle in semicircle. No matter where we come off a diameter, we always get a 90-degree angle in semicircle. Right, next up we're going to look at what we call angles in the same segment. Now the most important thing is to understand what a segment is. A segment is created by either a chord is the line that joins straight across, or an arc. Okay, so if we show the segments that are created by C and D, there they are. We've got a green one at the bottom and a yellow one at the top. Now if we show angles in those segments, all right, in that yellow segment, you will see that the 2 angles in the yellow segment are equal, no matter where we drag them. Right, some people call this the butterfly theorem, or the bow tie theorem. Okay, but it's called the angles in same segment theorem. Notice that if I drag point D, the segment actually gets smaller. The yellow segment's getting smaller, and the angle sizes actually get bigger. Okay, right, so that's how that theorem works. Okay, angles in same segment theorem. We can obviously also have different segments. So here's segments A, and the segment created by A and E, and I hope the colors are reasonably clear, but there's a little piece up at the top here, and if we show the angles there they are. They're both in the kind of blue segment, and because of that they will be equal. Okay, the next one is very similar. Now you're probably saying, Paul, this just looks like angles in the same segment, and it's very, very similar, but in fact what is happening here is that we've got two arcs or chords of the same length, okay? And so in fact these angles, these two 37-degree angles, are not in the same segment, but they are in the same size segment. All right, so it doesn't matter where we drag this, it will be equal to that one because it comes off a chord of equal lengths. All right, or an arc. The curved line is the arc, the straight line is the chord. Okay, notice that if we change the length of the chord or the arc, then the angles change size, but they change size together. They're both equal. Equal arcs subtend equal angles. Okay, all right. The next one we're going to look at is the converse of the angles in the same segment. And so what this says is that if we've got a picture like this, where we've got a 31-degree angle and a 31-degree angle, we can change that, right? Then we will always be able to put a circle through those points. In other words, there will be a cyclic quad. There's the circle. Those 4 points will be on the corners of a cyclic quad. So we can drag this, some of these points we can move around, some of them we can't. Okay, there we go. We can drag that. There will be a circle through those 4 points. Okay, that is the converse of angles in the same segment. The next thing we're going to look at is what we call a cyclic quad. And there are two interesting things about a cyclic quad. One is that the opposite angles add to 180 degrees. So in other words, these two blue angles, no matter where I drag them, no matter how I drag this thing, the two blue angles will add up to 180 degrees, okay? And the two red interior angles, the opposite ones, will add to 180 degrees. And then the final thing, obviously, is that the exterior angle must equal the opposite interior angle. And that follows, obviously, if these two have to add to 180 degrees, and these two add to 180 degrees, then this piece is kind of common, so these two pieces must be equal. Okay, right, exterior angle of cyclic quad. Okay, the next is the converse of that, and what that says is if you've got a pair of opposite interior angles that are supplementary like that, then obviously that one would be 119, so you've got an exterior angle. There will be a circle through those 4 points. In other words, that thing will be a cyclic quad. That's the converse, okay? Notice we can change the size of this. We can drag this around. This sketch has been made so that the exterior angle is equal to the opposite interior angle, or so that the opposite interior angles are supplementary. There will be a circle through those 4 points. Okay, the next and last three theorems deal with tangents. Okay, the first one just says that if we draw a radius to a tangent, it's always at 90 degrees. Okay, so we can see it doesn't matter where it goes, it's always at 90 degrees. Next one says, and sorry, that one we're going to use in our next module, which is actually on analytical geometry. That's going to be an important result there. The next one says that if we take a point and we draw tangents to the circle from that point, they will be the same length. So notice, it doesn't matter where I draw two tangents, they'll be the same length. Some people call this the clown hat or the ice cream cone theorem, because if you turn it on its side, it'll look a little bit more like an ice cream cone. Okay, and then the very last, well, second last one is the tan chord theorem. Okay, and what that says is that if we've got a tangent, this blue line is a tangent, the angle between the tangent and the chord is equal to the angle on the other side of that chord, the angle that chord subtends. It's called the tan chord theorem. It's also called the alternate segment theorem, and I actually prefer that name. All right, if we look at this green 55-degree angle, it's between this tangent and this chord. It's kind of in this segment over here, and it's equal to the angle in the other segment, the alternate segment, the other segment. Okay, and likewise the 63.6. Obviously, if I drag this, right, you'll see the green ones are changing. Okay, the pink ones are staying the same. If I drag this, you'll see the pink ones are changing and the green ones are staying the same. But have a look, the angle between the tangent and the chord is equal to the angle that that chord makes on the other side. Let's just move this around a bit. We can make the circle bigger. We can, and guys, often in a test or something, the diagram is going to be like that. Okay, you might need to turn your book to be able to see the tan chord theorem. But look at this. The angle between the tangent and the chord is equal to the angle on the other side subtended by that chord. And then the very last one, and this is to prove that something is a tangent. If these two angles are equal, then we have a tangent, right? So the tan chord theorem says if this is a tangent, then these angles will be equal. The converse says if these angles are equal, then we've got a tangent. In other words, if we make this, we can see right now that's definitely not a tangent. If we make this angle to 46 degrees, we will get a tangent. All right, and there it is, tangent. As soon as it's not 46 degrees, it's not a tangent anymore. So we can drag this thing around however we kind of like. Now we would need to make that angle equal to 37 degrees. When it's 37 degrees, we will have a tangent. There it is. Okay, we hope you found this useful. These sketches are all available on the CIMI website. If you just go to cimi.education, there's a page called Engage, and you can actually play with those sketches yourself, either on a phone or on a laptop. We really encourage you to do this because it helps you get comfortable with the theorems, okay? Every single one of these results is in your geometry workbook, okay, in your CIMI workbook. Let's just have a look. Okay, so there they are, all right? All the results that you need are all on these pages coming up in your workbook. Everything we've done. Here's the circle geometry stuff. You might remember we said that there are 4 different kind of flavors of the angle at center theorem. There they are on your screen there. Okay. In each case, the reason that you may use in an exam or a test is given in brackets after the theorem. Okay, so you'll see there they go, there they go, there they go. Right, now from here, it's just about practice. Okay, so before the next lesson, try some of these questions from page 31 onwards. And in the next lesson, we look forward to going over them with you. Have a great day, everyone.